Hello, this is Jack Jackson. Today we're going to be looking at equations and inequalities that have rational exponents in them or radicals. Now, in our previous work we have looked at the meaning of rational exponents and radicals. We started with just natural number exponents and extended that to talk about integer exponents and then fraction exponents, which are rational numbers. And then radicals are an alternative way of writing that. So, what we're going to be doing in this video is solving some equations that have fraction exponents and also solving some equations that have radicals. And basically we're just going to be doing a bunch of examples here. So along the way, every time we're going to check our answer and look for extraneous solutions, because it is possible to get those in some cases. And we're going to look at algebraic and calculator methods throughout the video. So one of the things that we want to be able to do, of course, is to be able to undo something, one of the key ideas of algebra. And we can undo a rational exponent on a base by raising the entire expression to the reciprocal of the original power. So if we have x to the n over m power, if we raise all of that to the m over n, the powers cancel and we're back to our original x value. And this fact can be useful and helpful in solving certain types of equations. If we can get one side to look like something to a power, then we can raise both sides of the equation to the reciprocal power, and then often that will give us something that we can that will help us or get us closer to an answer. You absolutely must check your answers in these examples. When we did linear functions, if you never made a mistake in working out the problem, your answer was always going to check. But that's not the case in some of the problems that we're going to be looking at in this set, because sometimes under certain conditions there are some powers that you can raise both sides to, and when you get done it looks like you're almost done. You think you have an answer or answers and it looks like they're good, but when you plug them into check, one or more of those answers don't work. Those are called extraneous solutions, or basically false extraneous roots, extraneous solutions, or basically just false answers. So you just have to eliminate those. So here's what we're going to do. We're going to look at some examples. So let's start with this one, x cubed equals 16. Solve this by hand. Also solve it using your calculator. Check it. And also let's give our answer both in fraction exponent form and in radical form if that's appropriate. So I think you can probably figure out what to do with this one. Go ahead and try this on your own. Press pause now. Well, the idea, as it always is with solving any equations, is to get the x by itself. So we've got this 3 and we want to eliminate this power of 3. So when we have a constant power and we want to eliminate it, we can eliminate it by raising it to the reciprocal power. So if I raise the left side to the 1/3 power, the powers will cancel and leave me just x. Of course, if I do that, I must raise the other side to the 1/3 power. Now, another thing that you notice I may have done, or I did do, right here at the beginning, is I took my number 16 and I factored it into prime factorization form. As we noticed in some of our properties of exponents and radicals, it's very useful when you're working with radicals and exponent properties to have our bases in factored form and get them down ultimately to a prime number base. And so that's what I did here. I got this down to that form. Then I did exactly what I said I was going to do. Take the 1/3 power of both sides. And then on the left side the powers multiply to get x to the first power. So that's just x. On the right side the powers multiply to get x to the 4/3, or get 4/3. 4 times 1/3 is 4/3. Now that's a perfectly legitimate way to leave the answer. And if you like fraction exponents, that's probably the way you're going to leave the answer, x equals 2 to the 4/3. And in many ways, one could argue that's the best way to write the exact answer. If you're going to write it in radical form, however, we want our radicals to be reduced, which means they basically need to correspond to proper fractions. So I want to put this in mixed number form. So we take 4 divided by 3, we get 1 with 1 remainder, so that's 1 and 1/3. Or 1 plus 1/3. Using our properties of exponents, that's 2 to the first times 2 to the 1/3, and the 2 to the first is just 2, of course, and 2 to the 1/3 could be written as the cube root of 2, So we get x equals 2 times the cube root of 2. So whether you write it as 2 to the 4/3 power or 2 times the cube root of 2, that is the same thing, and that's an exact value. If you plug either one of those versions into your calculator to get a decimal approximation, you get approximately 2.5198421. The decimal approximation at the bottom is an approximation. If you have a calculator that has 50 decimal places, it's still going to be an approximation because this is actually an irrational number. The exact values are the ones that I have boxed in there. Now, we have to check our answer. So our original equation was, look here in the middle, is the check. X cubed equals 16. Replace x by what it is, 2 to the 4/3. Now we use our properties of exponents. The exponents multiply together here and the 3's cancel. I get 2 to the 4th. 2 to the 4th is 16. 16 equals 16. That's true. So it does check. Okay, so that's an algebraic method on the left column. An algebraic check in the middle. Both of those are done by hand without aid of any calculator except for finding that decimal approximation, which if I have you do something like that, that'll definitely be a calculator problem. Now we can also use our calculators if we have them to actually find the decimal approximation. It will not find the version 2 to the 4/3 or 2 times the cube root of 2, but what it will find is a decimal approximation. So, as we recall from solving linear equations, remember when we solve linear equations we said some of the techniques that we're going to learn there are going to apply to any other type of equation. And one of the techniques we learned there was to let y1 equal the left side of the equation, y2 be the right side of the equation, and see where the two graphs cross. And if you look at the screenshots from a TI-84, you'll see I did exactly that. I'll let y1 be x cubed and y2 be 16. I use this particular window that you see here, and all I need is some window where I'm pretty sure I have all the places that they cross. And it looks like from this graph here, this is coming up, increasing all the time. This is horizontal. It's only going to cross that one time. And so you do a calculate intersection. So that's second trace for calculate, number 5 I believe for intersect, and then you identify first curve, second curve, and a guess, and then the output is what you see here. And notice that's the same decimal approximation that we got by plugging in 2 to the 4/3 power on our calculator. By the way, if you do this 2 to the power 4/3, be sure you put the 4/3 in parentheses. Okay? And of course the 16 here is of course what both sides equal in the check. Okay? Let's go on. Alright, here's another one, very similar one. See if you can solve this one yourself. Go ahead and press pause now. Okay, well now you're back. I think you see that, again, the first thing I'm going to do is factor out the 32. It's actually 2 to the 5th power. You can do a little factor tree on some scratch paper if you need to for that. And then I raise both sides to the reciprocal power of the power that's on the x. So I've got x to the 5/3. I want x to the 1st down here. So if I can multiply that 5/3 times 3/5, that would cancel out. I can multiply the powers if I raise the left side to that power. And of course if I do that, I need to do the same on the right. The 5's and the 3's cancel here, leaving you just an x to the 1st power. Over here the 5's cancel on the right, leaving you just the power 3. So x equals 2 to the 3rd. Of course 2 to the 3rd is another way to just say 8. So x equals 8 is the correct answer. Let's double check that. 8 to the 5/3. 8 is 2 to the 3rd. The 3's cancel here, and you get 2 to the 5th, which is 32, so that checks. Again, we could find this one. This one we can, since it's a natural number here, or an integer, we should be able to find this exactly with the calculator. And so again, we let y1 be the left side, x to the 5/3 power. Notice I put parentheses around the 5/3. If I don't put parentheses around the 5/3, I only get x to the 5th, and then the whole thing is divided by 3. I want to do the division first, so I put that in parentheses. And then y2 is the right side, which is 32. I need to experiment maybe a little bit, or think about what I know about the graphs a little bit, or look at the table, or somehow or another come up with an appropriate window. Sometimes that's a little bit of a trial and error process, but we come up with an appropriate window. Here's one that'll work, and we graph it, and you can see this this shape here. So it actually is going down here. Some of this has got the words over it, but there's some graph down here in the 3rd quadrant, and it's coming up this way. Okay, well, calculate that intersection, and it's 832, so x equals 8. Alright, here's another one. See if you can do this one. Press pause now. Well, the first thing to do is to get the x to the 1/2 on the side by itself. So we're going to add 7 to both sides, and then we'll go from there. So I just added 7 to both sides. I can get x to the 1/2 equals 16. The reciprocal of 1/2 is 2, so if I raise each one to the second power, I'm going to end up multiplying the exponents. Now, of course, what I'm really doing is squaring all this, but you do it by multiplying the exponents, and we just get x. And then on the right, we get 16 squared, which is 256. Anytime you raise to an even power, you for sure have to check these. So we want to just get in the habit of always checking these no matter what when they have these exponent things. If you raise to any power, let's just say you're going to check them. Okay? So we're going to check that by plugging in. 256 is 16 squared. The square root of that would be just the 16, or the 1/2 power of that would be 16. 16 minus 7 is 9. 9 equals 9. It does check. It's also going to check by doing it in the calculator. So again, we let the left side be the y1. So that's x to the power of 1/2 minus 7. Notice the 1/2's in parentheses. And then y2 is 9. Pick a window, and we have to go way out to the right on this one because the correct answer is 256. But with a little bit of trial and error, we can get it out there and calculate the intersection, and sure enough, x is 256. Alright, try this one. Very similar to the last one. Press pause now. Well, again, the first thing we're going to do is add 7 to both sides, and we get x to the 1/2 equals -5. And if we just keep proceeding by squaring both sides, we'll get x equals 25. So it looks like that's the solution, but if you look, it doesn't check. If we plug 25 in place of x here, 25 to the 1/2 is 5. 5 minus 7 is -2. -2 equals -12. I don't think so. That's false. So that means the one potential solution we had doesn't work. So this is a no solution situation. Basically, the problem is when you raise things to the second power. Raising to the second power is a function, but it's not a one-to-one function. And so when we reverse this, we can introduce some answers that are incorrect. Now, we could have actually stopped right here at the first step after we do this red one here. As soon as we got to x to the 1/2 equals -5, we could have gone ahead and stopped and realized that there was no solution if we'd been paying attention there, because we know that when we take the 1/2 power or square root of any real number, we never get a negative number, right? We might get an imaginary number, we might get a positive number, we might get 0, but we never get a negative number. And so that's not possible. So the answer is that there is no solution. And of course that means the two graphs are not going to intersect when we do it with the calculator method. On the left, let y1 be x to the 1/2 minus 7, and the part on the right, -12, be y2. And we graph those, and we see that this graph starts on the x-axis here at 0, -7, and it's increasing concave up as we go on to the right, and this y equals -12 is down here, and they just don't meet, so there's no solution. Alright, try this one out. Press pause now. Well, we just want to raise both sides to the 3/2 power, and they multiply together and cancel out. And on the other side, the 2's cancel, and we get 2 to the 3rd, which is 8. The problem with this is we have to be real careful on the one on the left side. So anytime you raise both sides to a fractional power with an even denominator, and then reduce it, then you need to introduce absolute value. So the fact that this thing on the outside had a 2 in the denominator, that tells us that we need an absolute value. Okay? If we go back, notice that didn't happen on any of the ones before. Okay? This is a 1 in the denominator, 2 over 1. This one's 3 over 5. It's an odd number in the denominator. Okay, back up. This one is a 3 in the denominator. So the examples that we were looking at earlier, that didn't happen for us. But this is the first one where we have an even number in the denominator. So when we have that, we have absolute value. Well, so it says the absolute value of x equals 8, so either x equals 8 or x equals negative 8. And if you look, they'll both check. Whether you have positive or negative 8, that's either negative 2 cubed or positive 2 cubed. Either way, when we do this, the cubes cancel and we square it. But here's the deal. When this even power here, whether this is positive or negative, when we square it, it's going to be positive 4, and it is going to check. Now we can also see the check and see that it has two answers by looking at the graph. Okay, so if you let y1 equals x to the 2/3 and y2 equals the right side, which is 4, pick an appropriate window and graph it. If you notice, these graphs cross twice. This one on the right side is when x is 8, as you can see here when I did a calc intersect. When I did a calc intersect here on the one on the left side, you see that it has x equals negative 8. Okay? Alright, so let's look at the next one. This one, we're going to use another property here for this one. We're going to use some factoring on this. And the factoring involved here is just the distributive property factoring, or common factor factoring. And we're going to use the zero multiplication property. So just to remind you, that says, remember the zero multiplication says if you have two factors multiplied together to be 0, one of the two factors has to be 0. So if we can get this in the form a times b equals 0, then either a equals 0 or b equals 0. And of course, getting it in the form a times b is called factoring it. So we want to get 0 on one side, which we already have, and we want to factor the part on the left and then go from there. Now when you do common factor factoring, you factor out x to the smaller power. So the x to the 1/3 is what we're going to factor out. So go ahead and do that yourself. Press pause now. Okay, did you do it this way? When you factor out the x to the 1/3, then of course you're dividing each of these by x to the 1/3 to get this. X to the 2/3 divided by x to the 1/3 will be x to the 2/3 minus 1/3, which is x to the 1/3. And of course x to the 1/3 divided by x to the 1/3 is 1. So if you distribute this back out, you'll get back what we started with, x to the 2/3 minus x to the 1/3. Now we have it in the form a times b equals 0. So you either get a equals 0 or b equals 0. The a is the x to the 1/3. So either you get x to the 1/3 equals 0, or you get the other factor, x to the 1/3 minus 1 equals 0. On the one on the right, I went ahead and added 1 to both sides of the equation, and now we're going to raise to the reciprocal power both sides there. So the reciprocal of 1/3 is 3, so we're going to cube both sides. And we see x to the 1/3 cubed is just x, and 0 cubed is 0. And again, x to the 1/3 cubed is x, and 1 cubed is 1. So we get x is 0 or x is 1. And we're going to check it. Notice that we never, when we actually did the part where we're raising to the power, we raised to an odd power. These should check. So let's see here. So if we have the x equals 0, you plug in 0 for x here and here. Okay, if you can see my cursor there. And of course, 0 to the 1/3 is 0. 0 minus 1 is negative 1. And 0 times negative 1 is 0. And 0 equals 0, true, so that checks. On the other hand, you can take the same original equation. Well, I took the factored version, actually. I probably should have used the original equation. And we plug in the 1. The 1's going to make this factor equal to 0. 1 times 0. You could have done it in the original one, too. If you plug in 1 in both of these, 1 to any power is 1, so you get 1 minus 1, which is 0, so that checks. And if you plug in 0, 0 to any positive power is 0, so you get 0 minus 0, which is also 0, and that checks. So, probably better speaking, I should have plugged in the original one. But it is kind of instructive to plug in this factored version because you see 0 makes one of the factors 0 and the other one negative 1. And 1 makes the other factor 0 and the original factor 1. So either way you go, one of the factors is 0, and so the product is 0. Now since it's 0 here on one side, instead of doing a calc intersect, we're going to do a calc 0 on the calculator. So you let that y1 be the left side, x to the 2/3 minus x to the 1/3. Figure out an appropriate window. Looks like that should be saying negative 5 to 5 and negative 1 to 1 for the window. And here's part of it. It's coming down this way, decreasing concave down. Somewhere in here it hits, actually goes through the origin, turns around, comes back up, and it goes through well, actually at 1 right there. And so how can we check that? Well, you do a calc 0. It's going to ask you for a left bound or right bound. So for this one here, we're going to give it something a little bit negative and a little bit positive, say between negative a half and a half. And we're going to guess maybe something in the middle like 0, and sure enough, it actually is 0. And this one here, maybe we could say, okay, well, it's between a half and 1.5, or a half and 2, or something like that. We guess something close to 1, and sure enough, exactly 1 works. Alright, so we've done some with equations with fractions, exponents in the equation. Now let's do some with radicals in the equation. Remember, a radical is really just a fraction exponent in disguise. So the same basic technique is going to work. We're just going to raise both sides to 1 power. In fact, one thing we could do is just switch it right away to a fraction exponent and work it that way. I've chosen these examples to leave things in radical notation, and that's another option. So really you could do it either way. So let's try this one now. Press pause. Well, this is the square root, so it's a second degree radical. That's like a 1/2 power. So if we'll raise that to the second power of the square root, and the square will cancel each other. Of course, I have to square both sides. 1 square is still 1, and the square root cancel. The square and the square root cancel, leaving you 4x minus 17. We have to add 17 to both sides and divide by 4, reduce that fraction of 18/4 down to 9/2, or in decimals, 4.5. Now, this is one where we're squaring, raising to an even power on both sides. You absolutely have to check these, because we can have an extraneous solution here. So we plug in 9/2 for x and work this out. Let's see, the 2 and the 4 cancel down to a 2 times 9 is 18. 18 minus 17 is 1. Square root of 1 is 1. 1 equals 1. All is right with the world. It does check. Again, if you have a calculator available to you for a problem like this, you can also do it on your calculator. Okay, in this particular one, we can actually do it exactly. We can let y1 be the square root of 4x minus 17 and y2 be 1. Pick some window, a zoom standard just worked for this one, and then do a calc intersect, and you can see the intersection is 4.5 for x. Of course, y is 1. But the important part is x equals 4.5. If you wanted at this point to do this, you could go quit. So that's second mode on the 84. That would be quit. Then type x, and it would be 4.5. You can change it to fraction form, and that would get you to 9/2. So if the problem has a nice fraction answer, a fraction answer where the denominator is not too big, then in fact the change to fraction thing with the calculator will work, and you can get an exact answer for those cases. If the answer is an irrational number, which it often is, then this technique the algebraic techniques are the ones you have to use to be able to get the exact answers, which will maybe have some roots or powers in them. Alright, here's another one. See if you can do this one. Press pause now. Okay, well, the trick is to get the radical on one side by itself, or the fraction power on one side by itself. So I'm going to add 4 to both sides to get 11 on the right and just get the square root by itself. Then I'm going to undo the square root by essentially raising to the reciprocal power. That square root is a 1/2 power. I'm going to raise to the second power. Again, I'm raising the second power, so I could be introducing extraneous solutions, so I need to check it. So see here, I added 4 to both sides. Then I squared both sides. 11 squared is 121. Here the square and the square root cancel, giving you 5 minus x. Subtract 5 from both sides to get 116 there, and divide both sides by -1 to get x equals -116. We can check that by plugging that in, which we have to check it. 5 minus -116 is 5 plus 116, which is 121. The square root of that is 11. 11 minus 4 is 7. 7 equals 7. That's true, so it does check. Again, the calculator solution, y1 equals the left side, y2 equals the right side. Experiment a little bit with the window, and there's a window that works where it shows the intersection, and kind of convince yourself that's the only place they could intersect, and do a calc intersect, and sure enough you see the correct answer. Alright, here's another one for you to try. Try this one. Press pause now. Well, this time when we subtract 3 from both sides, we get -2. Square both sides, you get cancels out the square root, so you get x plus 9 equals 4. Subtract 9 from both sides, we get x equals -5. Now we check it. -5 plus 9 is 4. Square root of 4, principal square root is 2. 2 plus 3 is 5. 5 equals 1. Uh-oh, that's false. So that means we have to throw out that potential solution, and in fact there were none left, so there is actually no solution to that at all. So when I graph this, my graph should not cross at all. And so notice I put y1 equals the square root of x plus 9, and then plus 3, and then y2 is 9, and graph them, and notice that y equals 1 is a horizontal line, okay? But the other part is an increasing function, but it has an endpoint on the left. It has an arrow on the right, but it's going up as it goes to the right. So they never cross, so that means you have no solution. Now, we could have stopped actually at the red part right there, the second step where we had square root of x plus 9 equals a -2, and realize once again that when you take the square root of a real number, and notice, by the way, we are talking about only real numbers here, you never get a negative number. You could get 0, you could get positive, you can even get an imaginary number, but you never get a negative number. Okay, this one's similar, but it's a cube root. Go ahead and do this one now. Press pause. So we're going to subtract 6 from both sides to get 2. Then we're going to raise to the reciprocal power. The cube root is the 1/3 power, so we're raising both sides to the 3rd power. And so that gives you 5x plus 6 on the left and 2 cubed, which is 8, on the right. Subtract 6 to get 2, and divide by 5 to get x is 2/5, or in decimal form, 0.4. Check it by plugging in 2/5 for x in the original equation. Notice the first thing you do when you multiply 5 by 2/5, the 5's cancel and leaves you 2. 2 plus 6 is then 8. The cube root of 8 is 2. 2 plus 6 is 8. 8 equals 8. It is true. Again, we can use a calculator solution. Let y1 be the left side of the equation. Let y2 be the right side of the equation. And just see where they cross. And by doing a calc intersect. And you can see that it comes back with 0.4 for x. Of course, y is 8. If you quit now and just type x, you're just going to be 0.4 as long as you do it right after you did that calc intersection. And now if you change that to fraction, you can see the answer in fraction form, which is 2/5. So since this one is a terminating decimal, both the 2/5 and the 0.4 are actually exact answers. Let's try another one. Try this one. Press pause now. Okay, first thing we're going to do is subtract 7 from both sides because we want to get that radical isolated by itself. Now square both sides for the square to cancel the square root out, leaving the left side as x minus 5. The right side, alright, now we got to do a little bit of algebra here. X plus 7 squared, you square the first term, x squared, you square the last term, plus 49, and to get the middle term you multiply the two and double it. X times -7 is -7x, and double it is -14x. Or just do x minus 7 times x minus 7 using the distributive property or FOIL or law of multiplication. But anyway you get it, you get the right side expanded out. Now I'm going to subtract x from both sides of the equation to get -15x, and no x is on the right, and no x is on the left. And we're going to add 5 to both sides of the equations to get no constant term other than 0 on the left. And we're going to add, and when we add 5 to the right, 49 plus 5 is 54. So now I have 0 equals x squared minus 15x plus 54. Now you want to factor that with anti-FOIL factoring. Okay? Then we first times first, let's get the f to work. First times first has to be x squared. So to get the middle term to work, you're going to need to split that up as an x and another x. The O, the L part is -6 times, or is 54. It's got to be 54. So what are our possibilities here? You either have 1 and 54, or -1 and -54, 2 and 20. Let's see, 2 and 27, 3 and 18, or 6 and 9. In fact, they're both going to be negative because their product's got to be positive, but the middle term's negative. So if you look at those, the ones that get the O and the I to work out would be the 6 and the 9, or negative 6 and negative 9. So we have this factors is x minus 6 times x minus 9. Do FOIL and check it out. X times x is x to the 6. Negative 6 times negative 9 is 54. The inner product is negative 6x. The outer product is negative 9x, which adds up to negative 15x. So now we have it in the form 0 equals a times b. So either a equals 0 or b equals 0. The a is x minus 6. The b is x minus 9. So we have either x minus 6 equals 0 or x minus 9 equals 0, which means x equals 6 or x equals 9. But notice we raised to an even power. We must check our answers. In this case, one checks and the other one doesn't. Okay? So if we check the x equals 6, we plug that in for x, and we get 6 minus 5 is 1. Square root of 1 is 1. 1 plus 7 is 8. 8 equals 6. That's false. So that does not check. When we plug in the 9, now remember there's a 9 on the right side there in place of x, and also 9 under the radical there. And so we get 9 minus 5 under the radical. That's going to be 4. The square root of 4 is 2. 2 plus 7 is 9. 9 equals 9. That is true. So the x equals 9 checked, but the x equals 6 did not check. So the x equals 6 is what we call an extraneous solution or an extraneous root. Basically just a false answer, one that doesn't really work. So you have to throw that out. The one that does check, of course, that one works. So x equals 9 is the only answer. We can see that there's only one answer when we graph it. Let y1 be the left side, which is square root of x plus, square root of x minus 5 in parentheses, and then plus 7. And the right side is just x, so that's y2. And graph these two. Again, you may need to experiment with the window here. You can see the window I used. I think I probably did a zoom square or something at some point to get these particular numbers. But anyway, I've got those in there and did a calc intersection, and you see only one point of intersection, and sure enough, x is 9 and y is 9 there actually as well. But x is 9 is our solution, the one and only solution. Alright, here's another one for you to try. Press pause now. Come back when you got it finished. Okay, so by now, for sure, you should be doing these as we go along. If you weren't doing them before, certainly you've seen enough examples you should be able to do this. So if you haven't, go ahead and press pause and do it. And if you have, now we're back to check out our answer. So we want, we've got a fraction exponent, and we want to get that expression by itself on one side. So we're going to add 2 to both sides, and then we're going to raise to the power by the reciprocal power. So the reciprocal power is 3/2. Okay, so we got 2 to the 3/2 on the right. The 3/2 and the 2/3 cancel and give us x minus 5, but it needs absolute value. Okay, so now remember, when the denominator on this power on the outside is an even number, that's when you use absolute value. That's a little technical thing that you got to remember there. Because if it's an odd number in the denominator on the power on the outside, then it does not have absolute value. But if it's an even number, it does need it. Okay, particularly when there's an even here and we cancel. Okay, so it's at the point when we do the canceling actually that we have to introduce the absolute value. And so we see that. Okay, well the absolute value equals something. That means the absolute value of whatever equals 2 to the 3/2. That means the thing in the absolute value could be 2 to the 3/2, or it could be the opposite of 2 to the 3/2, and it would still have the same absolute value. And then finally add 5. So if you like fraction exponents, you'd write it like this first box. X equals 5 plus 2 to the power 3/2, or x equals 5 minus 2 to the power 3/2. If you'd rather have radical notation, remember 3/2 is 1 1/2, so that's a 2 to the first and a square root of 2. So in radical notation, you'd write that as reduced radical notation. That would be x equals 5 plus 2 times the square root of 2, or x equals 5 minus 2 times the square root of 2. If you plug these in your calculator, either the fraction exponent form or the radical form, please do that to check it. Either way you go, you're going to get these decimal numbers down here as approximations. So the one with the plus 5 plus 2 square root of 2 is approximately 7.828427125, and the 5 minus 2 square root of 2, or in other words 5 minus 2 to the 3 halves, is approximately 2.17157285. And these are irrational numbers, so they do not terminate or repeat, actually. So these are approximations when we do them in the decimal form. Now, again, we need to check our answer. So it looks like I used the radical version to check. I could have used the fraction exponent version to check instead. But whether you plug in 5 plus or minus 2 times the square root of 2, this set of parentheses on the inside just kind of drops out. And we notice that the 5 minus 5 cancels each other out to be 0 plus 2 square root of 2x gives us 2 square root of 2x. Or no x, 2 square root of 2. Okay? And so it's plus or minus 2 square root of 2. Now, I went ahead and put it in fraction form. Okay, that's 2 to the 1 half. And then 1 plus 1 half is 3 halves. And now when I raise this, notice that the cubes can't cube and the cube root cancel. But then when I'm squaring something, it's going to, whether it's positive or negative here, when I square it, I get a positive. So the 2 and the 3 cancel. But whether you have positive or negative, we end up squaring at the end here when we're checking it. So we're going to get a positive 2 here. And 2 minus 2 for sure is 0. And 0 equals 0, so it checks. Now, again, to see that there are two answers, we can graph it as well and figure out those answers, at least approximate answers, from the graph. Okay? So, since I have 0 on one side, we're going to do this not with a calc intersect, actually like it says here, but we're going to do a calc 0, in fact. So what we're going to do is we're going to graph the y1, or I did it y2 this time, is the left side, and then that'll be the only thing we graph, and then we'll see where it crosses the x-axis. So y2 is parentheses x minus 5, close parentheses, to the power, open parentheses, 2 divided by 3, close parentheses, minus 2. Notice I put the power in parentheses. Got to remember to do that. Pick a window. This says, there's a box over it, but it means negative 10 to 10. That's just a standard window. I just did a zoom standard, and I could see, in fact, the places where it crosses the x-axis, that there are 2 of them, and they were on screen, so I could figure this out. Then I just want to do a calc 0, which is second trace, and then choose, I think it's number 2, calc 0. It's going to ask you for a left bound. You go to the left side, somewhere over here, hit enter, then somewhere over here to the right, hit enter, and then somewhere close to the point of intersection and enter it, and we get this 2.17. And similarly up here, the other one, go left and right of this root and get close to it and calc, and or hit enter, and it's going to give you about the 7.8 something. And if you notice, those are the same numbers I got by plugging in my calculator, just 5 plus 2 times the square root of 2, or 5 plus 2 to the power 3 halves. I would like you to do this on your calculator and check this out. Make sure you know how to do this so that you're comfortable working with these things on your calculator, as well as being comfortable with working them by hand. These kinds of questions could show up on the no calculator part of the test. They could show up on the calculator part. If it's the no calculator part, I'm not going to be looking for these decimal answers. I'm going to be looking for exact answers. If it's on the calculator part, I could be looking for the exact answers and or the decimal answers. If all I need is a decimal answer, then the calculator solution is completely sufficient, because it will give me approximate answers, but not necessarily exact answers. Now, I want to do, before we leave, I want to do at least a couple of inequalities. In fact, I'm going to do one that's related to this. So I'm going to take this same thing and replace that equal to with a less than, or maybe with a greater than. And so there's what we have. Can you solve this one? Think about it. The boundary point of our interval, we're going to get intervals here like we did when we had inequalities before, but the boundary point are where these are equal, and that we already have solved. See if you can work this out now. Well, the boundary point is when we have an equal 0, which we've already worked out to be 5 plus 2 square root of 2, and 5 minus 2 square root of 2. So the graph, when you think of it as y equals, the left side here, you get this little, bird-shaped graph or whatever, and you have these points here. This one at 2.17 whatever, which is really at 5 minus 2 square root of 2, and this one over here to the right is really at 5 plus 2 square root of 2. It's about 7.8 something. Okay? Well, between there, the y value, which is the left side, is less than 0. So when I make this a less than, we're looking between these 2 points. So these two open circles here, 5 minus 2 square root of 2 and 5 plus 2 square root of 2, are the two places where this graph up here crosses the x-axis. And between those, the graph is below the x-axis. So when you're saying this function here on the left is less than 0, or y equals this thing on the left is less than 0, you're saying y is less than 0 on the graph of that function. That's when the graph is below the x-axis, and that's between these two values. And so that's shaded here on the x-axis or on a number line. On the other hand, when you do greater than here, you're wanting the graph up here in the corner to be above the x-axis. You're wanting the y's on this graph to be positive. That's when you're above the x-axis. So it's going to be this part here from negative infinity up to that first intersection or first root, which is at 5 minus 2 square root of 2. And then union from, so it goes below for a while, and then it hits 0 again at 5 plus 2 square root of 2 and goes from there on to infinity. And since neither one of these had the or equal to part, these are all open circles at the endpoints, and we get a graph like this. So it's to the left and to the right, but not this part in the middle. Now, what if you don't have a graphing calculator or you don't want to draw the 3D graph? Well, you can still do it. You just go ahead and figure out this equation, and we find our two, put these in order, and if we're going to really put it on number line, we need to kind of have some rough idea of what these decimal approximations are to get it graphed really in the right place on our number line. But if we don't even put a scale on our number line except for those two numbers, we can at least have those two numbers there. Now, it helps to have some idea how big these things are so we can know where some test points are. So, for example, we could test the point 0 and see what happens. 0 minus 5 is negative 5. Negative 5 to the 2/3. See what that is. That's the cube root of 25 minus 2. And that's actually greater than 0. So that's going to be shaded down here, but erased. Shaded down here for the greater than, but erased for the less than. And of course, if 0 is erased, then so is this entire interval from negative infinity up to this endpoint. And down here on the bottom in red, since that 0 is shaded, this whole piece to the left is shaded. We did a test point here in between, like pick 5. That'd be an easy one to check. Pick 5. 5 minus 5 is 0. 0 to the 2/3 is 0. 0 minus 2 is negative 2. Negative 2 less than 0 is true, so it gets shaded for the less than. It's a blue dot right here, and so that means you shade all this part in between. It's not true for a greater than, so that means you erase that dot, which means you erase all of the points in between here. And similarly, we can check a point out here to the right, and so forth. Okay? So, after completing this section and working this objectives, what should you be able to do? We should be able to find exact solutions to equations involving fractional exponents and radicals, at least the ones where the methods of this section apply. Okay, and we can make up equations where the algebraic techniques in this section do not apply, but you can see there are some equations where they are helpful. And then, whether or not the equations can be solved algebraically, we should be able to find approximate solutions of equations using a scientific graphing calculator. And of course, once you find the solutions to equations, we can find those as the boundaries of solutions to inequalities. And so we want to be able to use these same techniques to solve inequalities involving fractional exponents and radicals. So we have kind of expanded our idea of the kinds of equations that we can solve, where we've used some algebraic techniques where we've been able to manipulate and use some of our properties of exponents that we've derived earlier. And of course, we've also used some of our techniques that we learned back from linear equations. We've extended those techniques as well, including both some algebraic and some calculator techniques.